Good evening, everyone. I hope I am audible and visible, loud and clear. So, a very warm welcome to all of you for the first class of GATE Aerospace Engineering on YouTube. As you guys know that recently we have launched GATE Aerospace Engineering course for all the aerospace engineers. If you are also interested in GATE 2027 Aerospace Engineering, you can enroll in that batch. But for GATE 2026 students, we wanted to do something, so we started this YouTube series where we are going to cover all the important topics. In every session, we are going to cover one topic. We are going to cover the theory as well as the numericals, PYQs related to that topic, so that topic will be clear to you, and if you have already covered it, it will be revised. Good evening, very warm welcome to all of you. And today I have picked a very important topic related to structures, that is torsion in thin walled members. If you have seen the PYQs of GATE Aerospace, lot of numericals are there from torsion in thin walled members. You know the concept of torsion in solid shafts, but how to calculate stresses and deformations in thin walled members, that we are going to understand in today's session. Now, before we start, if you don't know me, let me introduce myself. My name is Apuroop, All India rank 320 in GATE Mechanical back in 2010, and I decided to pursue MTech from IIT Kharagpur, and my specialization was mechanical systems design. Then after that I was placed at Mahindra Research Valley, where my work was related to the design of cars. So I served there for 2 years before quitting my job and starting to teach. So I have been teaching for more than 10 years in the field of GATE and ESE, and I teach subjects like engineering mechanics, strength of materials, theory of machines, vibrations, etc. Now you guys know that strength of materials and engineering mechanics and vibration is also there in GATE Aerospace, and it is covered in the section of structures, right? Now, if you want to discuss any doubts with me, then you can join my Telegram group. This is my personal Telegram group. You can either search this name, or you can just scan this QR code in order to join this. You can send all your doubts regarding your preparation, regarding the subjects of structures. Okay, chalo. So without any delay, let's begin today's session. First of all, let's revise the concept of torsion in solid circular shafts. If you haven't done this, no issue, you can still watch this session. So let's say you have a circular cross section shaft, okay, and it is subjected to torque. If you don't know what is torque, let me show you physically. Let's say this is a shaft, it has a circular cross section. If you apply moments on the shaft like this, if you apply moment about an axis perpendicular to the cross section, this is the cross section, this is the axis perpendicular to the cross section. So if you apply moment about this perpendicular axis, then the effect that you get is known as torsion. This effect of twisting is known as torsion. Okay, so let's say we have a circular shaft, it's a solid shaft, and it is subjected to twisting moment T. Okay, this is the cross section of the shaft. What is this? This is the cross section of the shaft. Okay, it is subjected to twisting moment. Okay, now in order to calculate the stress and deformation, we derive the torsion equation, which is given by T by J equals to tau by R equals to G theta by L, where T is what? It is the twisting moment, torsional moment, right? What is J? J is known as polar moment of inertia. Moment of inertia about this axis, normal axis. Okay, for solid shaft, the polar moment of inertia is pi by 32 d to the power 4. Okay, Tau is the shear stress at any distance r. What is this r? Let's say this is the center of the cross section. So if you want to calculate stress, let's say at this point, then from center to this point, this radial distance is known as r, right? Maximum stress is developed on the surface because r is maximum on the surface. So at every point on the surface, tau is equal because at every point on the surface r is same. So tau will also be same, right? What is G? It is modulus of rigidity. L is the length of shaft. And what is theta? Theta is known as angle of twist. What do we mean by angle of twist? When you apply twisting moment, the cross section of the shaft is twisted by some angle. Let's say earlier the point, let's say P was here, and now the P point is here. So this angle by which it is twisted is known as angle of twist, right? So using this equation, we calculate the shear stress tau and the angle of twist theta. We can also use this same equation in case of hollow shafts, right? But if let's say you have thin walled members, then how you calculate the shear stress and the angle of twist? What do we mean by thin walled members? See, thin walled members are of two types. You can divide thin walled members into two categories: closed section and open section. So let me give you an example. What do we mean by closed section thin walled members? See, if you have thin walled members and the cross section is forming a closed loop, let's say like this. This is the cross section of the member, and you can see that this cross section is closed, right? So this is known as a closed section thin walled members. The thickness must be very low compared to the other dimensions of the cross section. Okay, so let's say this is the width, this is the height. Then compared to the width and height, this thickness is very less. Okay. Then we have open section thin walled members. Now what do we mean by open section thin walled members? Let's say you have the cross section something like this. So it's a C-type section. Okay, this is another thin walled member. Here also the thickness is very less, but this is not forming a closed loop. Okay, this is called open section. It is not completely closed, right? So this is an open section. Okay, usually in aircrafts, whenever there is a member which is subjected to torsion, we prefer closed section members because these type of members have better torsional rigidity, better torsional strength. Okay, they can sustain better torsional moments compared to open section. In case of open section members, the torsional rigidity as well as the torsional strength is less, so they cannot bear that much amount of torsional moment compared to closed section. Then sir, why do we study open section? Because there are some sections which due to some reasons might be subjected to torsional moments. Okay, although they are not designed to sustain torsional moments, basically they are designed to sustain bending moments, but due to some accidents they might be subjected to torsional moments, right? So we need to understand how much torsional stress will be developed here if they are subjected to some torsional moment by accident. How much torsional stress, how much shear stress will be developed in these type of sections, that also we need to study. Okay, so we have these two types of sections. In case of closed section members, the calculation of torsional shear stress as well as the angle of twist is comparatively easy compared to the open section members. Okay, here the calculations are complicated, little bit tricky, but in case of closed section, by making some assumptions, the calculations become very easy. Okay, you will also find most of the questions are from closed section. Okay, but also there are some open section problems also in GATE PYQs. Okay, so you will find both types of problems in GATE PYQs, closed section as well as open section. Okay, we are going to solve GATE PYQs also in today's session, and let me tell you, by the end of this session you will be able to solve all GATE PYQs related to this thin walled members. Okay, chalo. So let's first consider torsion in closed thin walled members. Okay, we will derive the equation of stress and angle of twist, and then we will solve some problems. We'll also solve some GATE PYQs. Okay, so let's say we have a shaft like this. Okay, it is subjected to some twisting moment, and the cross section you can see is thin walled. Okay, it's an irregular shape. It is not completely circular or rectangular. I am considering a general section. Okay, because whatever equation we will derive, you can apply this equation to any type of section, be it rectangular or circular. Okay, whatever the shape of the section is, we can use the same formula. This formula is only applicable for circular cross sections. It is not applicable to rectangular section, but whatever derivation we will do here, that formula can be applied to any shape. Okay, but it should be closed thin walled member. Okay, now let's consider a small element from the surface of this thin walled member. Okay, you can see I am cutting a rectangular member. Okay, and I am drawing it here. Can you see? Now, in case of solid sections, the shear stress tau depends upon the radial distance from the center. So the shear stress at this point and this point will be different because the R for both the points is different. But in case of thin walled members, we will assume that the shear stress across the thickness is constant. This is a very important assumption. What we are assuming, let me tell you, we are assuming that the shear stress at this point and this point, see, across the thickness, let's say this is the thickness, then from here to here the shear stress is same. Okay, so this is the first assumption that we are going to make, that the shear stress across the thickness is equal. Okay, but understand what is happening here. This is the member that we are talking about. Right? Now understand here. It is not necessary that the thickness of this entire section is same. Right? Here thickness might be different, here thickness might be different, here thickness might be different. I am saying that it might be something like this. If you look at the diagram of the cross section, it might be like this. Can you see? Here thickness is less, here thickness is more. Okay, so let's say that whatever member we are getting, the thickness here is, let's say, TA, and the thickness here is, let's say, TB. Okay, now I am assuming that the shear stress throughout the thickness is constant, right? Let's say here the shear stress developed is tau A. Now here the shear stress developed is, let's say, tau B. So due to this different thickness, the shear stress will be different. Here it will be tau A, here it will be tau B. Okay. Now, you know that the net force must be equal, right? Because in this direction, there should be no net force. So, the force developed due to this tau A and the force developed due to this tau B should be equal. Let's say that this length is dx. Okay. So, what will be this area? This area will be TA into dx. And what will be this area? This area will be TB into dx. So the forces are equal. The net force must be 0, right? The force developed due to this and force developed due to this should be equal. So what will be the force developed due to this tau A? It will be tau A multiplied by this area, which is TA into dx. And what will be the force developed here? Tau B into area. So tau B into TB into dx. Now this dx and dx will be cancelled. You are going to get this. Tau A into TA should be equal to tau B into TB. If the thickness is constant for the entire cross section, if the thickness is constant, then tau will also be constant. But if the thickness is varying, then tau will also vary. Okay. Now, we introduce a parameter here known as shear flow. What is this Q? Q is known as shear flow. You might have heard of this topic, you might have heard of this parameter shear flow, because this is a very important parameter when you are studying thin walled members. See, throughout structures you will study lot of topics related to thin walled members. You will study bending in thin walled members, shear in thin walled members, torsion in thin walled members, and in every topic this parameter will be there, shear flow. Now what is this shear flow? Shear flow is the shear force per unit median length. Median length means what? See, you can see that this is a center line, median line. Can you see? If this is the cross section, then this line is passing through the center of that cross section, right? So the shear force per unit length of this line is known as shear flow. If you multiply it by this length, if you multiply Q by this entire length, you are going to get the shear force, complete shear force. Okay, so it is shear force per unit length. Okay. Now, remember this equation, tau into thickness is equal to this Q, because the entire derivation will be in terms of this Q. Okay. Now we have to derive two things here. We have to derive the equation of shear stress tau and the angle of twist theta. What will be the shear stress developed at different points of this cross section, and what will be the angle of twist? If you apply a torsional moment here, how much angle it will be twisted by? Okay, so let's first derive the equation of tau. Okay, so you can see this is the cross section. What is this? This is the cross section. Okay, understand whatever is written here. This is the center line that I was talking about. Okay, so this is the center line. This is the centroid of this cross section. The axis passing through this centroid, we are applying the torsional moment about this axis. Okay, so you can consider this the centroid of this cross section. Okay, now let's consider a very small length on this line. Okay, on this line, let's consider a very small length ts. So we will derive the equation of tau using this very small length. Okay, let's say the force acting at this point on this very small length, the force, shear force acting at this point is dp. What is this dp? This dp is the shear force. Okay, now this shear force multiplied by the distance from this centroid will be equal to the torque developed by this force. So you can write torque dt equal to dp multiplied by distance from this point to this centroid is r. So what is this force doing? This force is creating a torsional moment. Okay, now this shear force can be written as shear force per unit length multiplied by length. So what is the length of this very small element? ts. So this shear force dp will be q multiplied by this length ts. So dt will be equal to q into ds into r. Okay, now this is the shear force on only this very small length. Similarly, there will be some force on this length, 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 right? And all of these forces together will create total torque T. This is only a very small amount of torque. Total torque is T. So how you are going to get that total torque? By integrating this equation, right? Q into R into ds. Okay, for the entire central line. Okay, now this shear flow is constant. This shear flow is constant means Q is same throughout this length. At every point the shear flow will be same, Q. Shear stresses are different at different points, but shear flow is same. Okay, so this Q will come out of the equation. Inside you are going to get this R into ds. Now look at this. This line is subtending this angle. Can you see this very small triangle here? The area created by this very small triangle is, let's say, dA naught. Can you see here? You can write it dAm. Okay, let me call it dAm. Okay. Sorry. Okay, let me call it dAm. So what will be this dAm? dAm can be written as half into base into height, right? So 2 into dAm will be equal to this R into ds, right? So from here T will be Q into integration of 2 into dAm. And how we are integrating it? How we are integrating it? We are integrating it for this entire length, right? So if you integrate these very small triangles, okay, let's say there is small length here, so you'll get another triangle here, small length here, so you will get another triangle here. So if you integrate this, you are going to cover this entire area, right? Area bound by this central line. You are going to cover this entire area. So beta, this integration will become this, where AM is what? AM is area enclosed by the middle line, right? This middle line is creating a closed area, so that area is given by AM. So this will give you the equation between torque and the shear flow, but we need the equation for shear stress. So Q can be written as tau into T, right? So T will be equal to tau into T into AM. So from here, sorry, not AM, to AM. So sorry, to AM. So from here, tau can be written as T upon 2 into T into AM. This will give you the equation of shear stress tau. Okay. How we are going to use this equation? Let's see. Let's say you want to calculate the shear stress in some thin walled member. Okay. Let's say this is the closed thin walled section and we want to calculate tau in this cross section. So what we are going to do? First, we will draw center line. Okay. What is this? This is the middle line. Okay. Then we will calculate the area enclosed by this central line. Okay. Let's say this area is AM. So you can calculate this area AM. Okay. Now let's say you want to find stress at this point. Let's say this is point A. So if you want to calculate stress at this point, you will put this thickness. Let's say this is TA. So what will be your formula? Tau at point A will be equal to T upon 2 into TA into AM. Okay, if you are calculating stress at this point, you will put this thickness. Let's say you are calculating stress at this point. Let's say this is point B. So you will put this thickness. Let's say this thickness is TB. So now your formula will become tau at point B equal to T upon 2 into TB into AM. Okay. If you want to calculate stress at, let's say, this point, you will put this thickness. If you want to calculate stress at this point, you will put this thickness. If the thickness is constant, then for every point throughout this central line, at every point, the stress will be same. But if the thickness is varying, then you will use this equation. Here you will put different thickness and you will get different shear stress. Okay. So this is how you can calculate the shear stress at any point in this member. Now remember, I told you that the stress across the thickness is same, means stress here, stress here, stress here. It will not be different. We are assuming that throughout the thickness, across the thickness, stress is equal. But along this line, the stress is varying, means at this point and at this point, stress can be different, because here the thickness is different, here the thickness is different. So here and here stress will be different, but at this line the stress will be same. Okay, now someone was saying that why this is not at the center, because beta, if this is not a regular shape, the centroid will not be exactly at the center, na? That's why it is somewhere here. Okay, it is just for understanding. Okay, it might be here, it might be there. Okay, now we have derived the equation of shear stress tau, but what about the angle of twist theta? For that also we need some equation. So the angle of twist theta is derived by energy method. Okay, we derive the equation of angle of twist using strain energy equation. You know that strain energy is given by force multiplied by distance, but we assume that the force is applied gradually. So the force versus distance graph is like this. So the area under this becomes half into force into distance. If you have covered the concept of strain energy, you might know this. Otherwise, don't worry, when you will study energy methods, you will learn this concept. Okay, so strain energy, let's say du, will be equal to half multiplied by force dp multiplied by, now when you will apply the force dp, what will happen to this rectangular element? You can see right now the rectangular element is like this, but when it will be subjected to shear force, it will twist by some angle. This is the angle of twist, this is the shear strain gamma. Okay, this is the shear strain gamma. So if this is the angle gamma and this is ds, then what is this? This is dx. Then what will be this distance? It will become gamma into dx. Okay, tan theta is equal to perpendicular by base, right? So this is the perpendicular and this is the base. So tan theta will be equal to gamma. So this perpendicular will become equal to base into gamma. So gamma into dx. So this is the distance by which it is moved. So the strain energy will be equal to half into force into displacement, and this displacement is gamma into dx. It's okay if it is a little bit confusing to understand, because you don't know the concept of shear strain or you don't know the concept of energy, so it will be difficult to understand this equation. But don't worry, after we will derive the formula, you will have to understand how to use that formula only. Okay, if you are able to understand the derivation, okay. If you're not able to understand, don't worry, when you will study all these other topics, you will be able to understand. Right now you need to focus on the formula and how to use that formula to solve the problems. Okay, now this force dp can be written as what? Q into ds, and this shear strain gamma can be written as shear stress divided by modulus of rigidity according to Hooke's law. So I will put tau by g into dx. Okay, now this tau can also be written as in terms of q. See here, okay, let's put tau in terms of t. So t is equal to q into t upon 2 into t into am. So du will be equal to half into Q is T upon 2 into AM. Okay, and tau can be written as T upon 2 into T into AM. Okay, this is the strain energy du only in this very small element. If I integrate this, I will get the total strain energy, and that total strain energy is also given by half into T into theta. How do we get this? See, there is a relation between torque and theta, linear relation between torque and theta, and the graph is something like this. The area under this is strain energy U. Okay, so this U is equal to half into T into theta. So if you put it and if you integrate it for the entire length, then you will get theta. I am directly writing the equation. Okay, otherwise if you want we can just put this value here. So it will be integration of, what will it become, T square ds into dx divided by 8 am square, 8t am square into g, right? This integration will be from 0 to L, where L is the length of the shaft, and this will be half into T into theta. Now this 1 T will be gone, this 4 will be gone. So from here this theta will be, now let me put the constant values outside. So T is constant, so that will come out of the integration. Okay, this will become 4 T am square into g. These are the constant values. If I integrate dx from 0 to L, I will get the length L. So it will become L. Now this will become this integration. Okay, T is also not constant. This will become integration ds by T. Now understand how to use this equation. What is this ds by T? This is the summation of ds by T for this entire length. Summation of ds by T for this entire length. Understand how to use this formula. Okay. I will again use the same example. Okay. Let's say this is the center line. Okay. Let's say this length is S1, this is S2, this is S3, this is S4. Let's say the thickness here is T1, this thickness is, let's say, T2, this thickness is, let's say, T3, and this thickness is, let's say, T4. Okay, so we have this varying thickness. Okay, so what will be the summation of ds by T? So it will be equal to, for this line it will become S1 by T1, then for this line it will become S2 by T2, then for this line it will become S3 by T3, then for this line it will become S4 by T4. If thickness is constant, means T1, T2, T3, T4, if all are same, then it will become S1 plus S2 plus S3 plus S4 divided by T. This thing will become S1 plus S2 plus S3 plus S4 divided by T. Means length of this center line divided by T. This thing will become length of the center line divided by T. But if the thickness is varying, then you will have to use this equation. Okay, theta is T into L, L is the length of the shaft, divided by 4 AM square into G. AM is what? It is the area enclosed by the center line into G, modulus of rigidity, multiplied by summation of ds by T. So using this equation we can find the angle of twist. So we have the equation of shear stress, we have the equation of angle of twist. Let's see how to apply these equations in order to solve the problem. If you have understood the derivation, very good. If you have not understood the derivation, it might be due to the lack of understanding of the other topics. Like if you don't know the concept of strain energy, you might not understand this equation. If you don't know the concept of shear strain, you might not understand how this is gamma. So all these small things you are not able to understand because the other concepts are not clear, but don't worry, if you study all the topics it will be clear. Right now just focus on using this formula in order to solve the question, in order to solve the problems. So let's solve a few problems. This is the first problem. You can see a thin walled member with varying thickness. Okay, these vertical members have a thickness of 6 mm and these horizontal members have a thickness of 10 mm. Okay, a torque of 5 kilonewton meter is applied to a hollow shaft having the cross section shown. Neglecting the effect of stress concentration, determine the shear stress at point A and point B. Okay, we need to calculate the shear stress at these two different points. Here the thickness is different and here the thickness is different, so the shear stress at these 2 points will be different. If the thickness was same, shear stress would have been same. So let's calculate the shear stress. What is the first step for calculating the shear stress? You need to first draw the center line. Okay, draw this center line. What will be the length of these lines? What will be this length? Horizontal line 75 minus 3 minus 3. Okay, this small distance is 3 mm, this small distance is 3 mm. So 75 minus 3 here minus 3 here. So it will be how much? 75 minus 6, 69. Then this vertical, this will also be 69. Then this vertical line will be how much? This is 125. Then this small distance is going to be 5 mm, half of 10, 5 mm. Then this small distance is going to be 5 mm. So 125 minus 5 minus 5, 125 minus 10, 115. This will also be 115. Okay, now we have drawn the center line, the middle line. The next thing that we need to do is calculate area enclosed by this center line. So beta, how much will be the area? It is a rectangle 69 by 115 mm square, right? Okay, so this is AM, which we will use to calculate shear stress at point A and point B. Now we will use the equation of shear stress tau, which is T upon 2 into T into AM. Here T will be same for both points, AM will be same, but the thickness will be different. So at point A, tau at point A will be T upon 2 into thickness at point A multiplied by AM. So what is the torque? 5 kilonewton meter. We need to convert it in Newton mm. So if you convert kilonewton meter into Newton mm, you will have to multiply 10 to the power 6. So 5 kilonewton meter is 5 into 10 to the power 6 Newton mm. Thickness at point A. What is the thickness here? 6 mm. and the mean area is 69 by 115. So how much will be the shear stress at point A? Can anyone confirm? 52.5099, rounding off to 2 decimal places, it will be 52.51 megapascal. Are you getting this? Can anyone confirm? $52.51 megapascal. Now, if you want to calculate shear stress at point B, all you need to do is just change the thickness. So this will become 2 into TB into AM. So the torsional moment is same. At point B, what is the thickness? It is 10 mm. So at point B, this will be 10 mm. AM will be same, 69 into 115. So tau B will be how much? 5 into 10 to the power 6 divided by 20 into 69 into 115. 31.50598, 31.51 megapascal. So at point B, the stress is comparatively less. Here it is 52.51, here it is 31. In this entire line, here and here, the stress will be 52.51, and here the stress will be 31.51 megapascal. Very good guys, very good. Okay, so we have calculated the shear stress. If you want, you can also calculate the angle of twist theta. We know the equation of angle of twist theta also, so we can use it to calculate the theta also. Okay, the G value is not given in this problem. Let's solve another problem. Maybe there we will get to calculate the angle of twist theta. Okay. Chalo. Next problem is from GATE 2020. Okay. A thin walled beam of constant thickness is shown in figure. See, here they have directly given you the center line. If this kind of diagram is given, it means they have given you the center line and the thickness is constant. If the thickness is varying, then this diagram will be given. If the thickness is varying, then they will give you this diagram. But if the thickness is constant, then they might give you this diagram, which is showing you the middle line, the center line. Okay. It is subjected to a torque of 3.2 kilonewton meter. Shear modulus means G is 25 gigapascal. Angle of twist per unit length is. Angle of twist per unit length means what? Angle of twist means per unit length means the length L will have to be unit. Now you can see that it is calculated in per meter. So L is equal to 1 meter, which is 1000 mm. Okay, 1 meter means 1000 mm. Okay, chalo. So let's calculate the angle of twist theta. Okay. Now, here, what is the equation of theta? Theta is equal to T upon 4 am square into G, T into L upon 4 am square into G, integration ds by T. As thickness is constant, as T is constant, this formula will become T into L by 4 am square into G S by T, where S is what? S is the length of the center line. Okay. So what will be the S here? 100 plus 400 plus 100 plus 400. 1000 mm. 400 plus 400, 800. 100 plus 100, 200. So total length will be 1000 mm. Just put the values here. So theta will be equal to T. What is the torque? 3.2 kilonewton meter. We'll have to convert it in Newton mm. So into 10 to the power 6. L should be 1 meter, means 1000 mm. Okay. Divided by 4 am square. What will be the area, beta? What will be the area? 400 by 100. Multiplied by G. Modulus of rigidity is 25 gigapascal. So 25 into 10 to the power 3 megapascal multiplied by S. S is 1000 divided by T. Thickness is 2 mm. So from here you are going to get the angle of twist per unit length. So what is the answer? .01 radian per meter. Are you getting this? 0.01 0.01 radian per meter. If they are asking you to calculate it in radian per mm, then here L will be only 1 mm. But here they are asking you to calculate it in radian per meter, and 1 meter is 1000 mm. So that's why I have to put L in 1000 mm. Okay, very good, Tushar. 0.01 radian per meter is the angle of twist. This was the question in GATE 2020 for 2 marks. Okay. Chalo. Let's move on to another question, and this was again from GATE 2019. Okay, GATE 2019 2 marks question. Let's solve this. A thin walled tube with cross section shown in figure is subjected to a torque of 1 kilonewton meter. Walls have uniform thickness of 1 mm and shear modulus 26 gigapascal. Assumed the curved portion is semicircular, shear stress in the wall is. So here this is again the center line. The center line is directly given. This time it is a different shape. So this looks like a triangle and this is semicircle. Okay. Now what will be the area enclosed by this and what will be the length of this? Let's first calculate the area and the length. Okay. So what will be the area? AM. If you want to calculate the area, you need to divide it into 2 regions. This is the triangle and this is semicircle. What is the area of triangle? Half into base into height, right? So half into base is 0.5 meter, or you can say 500 mm. Height will be 100 because the radius is 50. So this is equal to diameter 100 plus, for semicircle, for circle area is pi r square. For semicircle it will be 1 by 2 pi r square. So from here you will get the mean area. So I am getting 28926.99 mm square. Okay, and length of the center line also need to be calculated. Okay, we'll use this same formula again na. Acha, we need to calculate the shear stress only na, so we don't need the length. So directly we will use the formula of tau. So T upon 2 into T into AM. So what is the shear stress? 1 kilonewton meter. So 1 into 10 to the power 6 Newton mm. Okay. Then 2 into thickness. What is the thickness? Thickness is 1 mm. And the area enclosed by the center line 28926.99 mm square. So you are going to get the shear stress. How much is it? 17.28 megapascal. If you want, you can check with the answers also given by the official GATE website. You'll get the same answer. 17.28 megapascal. Very good, Supriya. So this is the shear stress in the entire cross section, 17.28 megapascal. Okay. Chalo. Shall we solve one more problem? So this is from GATE 2015. Another problem of GATE from GATE 2015. A thin rectangular tube is made of a material with shear modulus G equal to 80 gigapascal. Shear flow is calculated based on the mid thickness dimension. If the free end is allowed to twist no more than 0.0727 radian, means the value of theta is given. Maximum theta can be 0.0727 radian. Then the maximum torque which the tube can be subjected to at the free end is. So we have the value of theta, we need to find the value of torque T. Okay. So you will use the formula of theta. Okay. But first we need to calculate the area enclosed by the center line and the length of the center line. Here the thickness is not constant. For this vertical area, the thickness is 5 mm, and for horizontal one, the thickness is 3 mm. Okay. So let's first calculate the area and the length of the center line. 60 by 40. This is 60 by 40. Horizontal members have thickness 3 mm, vertical ones have 5 mm. Let's draw the center line. Now, what is the length of these lines? So, the vertical one 60 minus 3, 57 will also be 57, and horizontal ones 40 minus 5, 35. This will also be 35, right? 60 minus 2.5 minus 2.5. So 60 minus 5. Sorry, 60 minus 1.5 minus 1.5. So 60 minus 3, 57, and 40 minus 2.5 minus 2.5 means 40 minus 5, 35. Okay. Now we will have to calculate the area enclosed by the center line as well as the length of the center line. So area enclosed by the center line will be 57 by 35, right? And length of the center line will be How much? This is 1995 mm square, and 2 into 57 plus 2 into 35. This is 184 mm. These values are calculated. Now we need to put everything in the equation of theta. So what is the formula of theta? Theta will become T into L divided by 4 am square into G S by T. Okay, the thickness is here it will not be like this. So sorry. Thickness is varying na. So here we will have to use this formula. So sorry. Here thickness is not constant, it is varying, so we'll have to use this formula. Now understand, what is theta? 0.0727, right? So 0.0727. What is the torque that we need to calculate? But the torque need to be calculated in Newton meter. So I can write it T into 10 to the power 3 Newton mm. Let's say T is in Newton meter. So it will become T into 10 to the power 3 Newton mm. What is the length? Length of the shaft is given 2 meters. So we will convert it in mm, 2000 mm. Area enclosed by the center line is 1995. And what is modulus of rigidity? 80 gigapascal. So 80 into 10 to the power 3. Now summation ds by t. So understand how we are going to put. For these vertical lines, the length is 57 and the thickness is 5 mm, right? And we have two vertical lines. So 2 into 57 by 5. Then for horizontal lines, length is 35 and thickness is 3 mm. So 2 into 35, we have two horizontal lines, na? So this is going to be summation ds by t. I hope you all are clear about how to put the values here. Summation of ds by t. See, this is 57 divided by thickness 5. Again 57 divided by thickness 5. So 2 into 57 by 5. Similarly, for this 35 divided by thickness 3. Then 35 divided by thickness 3. So 2 into 35 by 3. Okay. Now in this entire equation, there is only one unknown, that is T. What is the answer? Thousand 3.518, or I can put it 52 Newton meter. 1003.52 Newton meter. Are you getting this answer? 1003.52 Newton meter. So this is the amount of torque that you can apply at the free end, so that the angle of twist will be maximum 0.0727. If you increase the torque beyond this value, then the angle of twist will exceed this value and this member will fail. Okay, so 1003, almost 1000 Newton meter is the answer. I hope all of you have got the same answer. Okay, so let's move to another question. But I think that by now you might have understood how to solve the problems related to closed thin walled members, right? You need to remember just two equations: the equation of shear stress tau and the equation of angle of twist theta, you need to know how to put the values in these equations. Okay, so we have solved problems where we need to calculate tau at two different points. Then we have solved the problem where we need to calculate theta and the thickness was constant. Then we solved this problem where we need to calculate tau and the thickness was constant. Then we have calculated the question where we need to calculate torque based on the angle of twist theta. So we have solved almost different varieties, every variety of problems that are there in your GATE exam. Now let's move on to torsion in open thin walled members. Let me tell you, open thin walled members are a bit tricky. The equations here are not easily derived. Okay, what are open thin walled members? Let me tell you, let me give you just one example right now. Let's say you have this L type section. Okay, let's say you have this L type section. Okay, so this is again a thin walled member, but this is not closed. Okay, so how to calculate the shear stress and the angle of twist in this case? So here, in order to calculate the shear stress and angle of twist, first we need to calculate the polar moment of inertia. And the polar moment of inertia here is calculated based on certain assumptions. So we will not get into the details of the derivation because it is a little bit complicated. We will see this derivation in other topics of thin walled members. Right now I will just directly write the equation of J. Okay, so in order to calculate the angle of twist and the shear stress, you need to first calculate the polar moment of inertia J, which is given by integration T cube ds by 3. You need to remember this formula, integration T cube ds by 3. Now how do we find this? How do we calculate this? Understand. Let's say this is S1 and this is S2. Let's say this is S1 and this is S2. Let's say the thickness, this thickness is T1, this thickness is T2. So what will be the equation of J here? J will become T1 cube S1 by 3 plus T2 cube S2 by 3. For this particular case, for this particular question, the polar moment of inertia J will become T1 cube, this thickness, into S1 by 3. Then for this T2 cube into S2 by 3. Okay, so this is polar moment of inertia. Once you get this, then you can easily calculate the shear stress tau and the angle of twist theta. How? Shear stress tau. The shear stress in the cross section can be calculated using tau equal to T into torsional moment T multiplied by T divided by J. For example, if you are calculating shear stress in this case, in this member, you'll put this thickness T1, and if you are calculating shear stress here, you'll put this thickness T2. Okay, and the angle of twist theta can be calculated using this equation. See, T by J equal to G theta by L. Remember, this we use in case of solid shafts. So from here theta is T into L by G into J, right? So here you can use this same formula. So all you need to do is calculate this J. Once you get this J, put the values here and you will get the equation of value of shear stress and the angle of twist. So tau will be T into T by J and theta will be T into L by G into J. This equation comes from the torsion equation. Okay. Chalo. This is the equation of polar moment of inertia is derived based on various assumptions. It is only true if the thickness is very small. Okay, this equation is derived based on the assumption that the thickness T is very small. Okay, so for thin walled members we use this polar moment of inertia equation. Okay, chalo, let's solve a few problems based on open section also, because in GATE PYQs you will find problems related to open sections also. Okay, so let's solve see a few problems. See, this is the first problem. A channel section shown in figure has uniform thickness. Uniform thickness means they have given the central line. See, they have only given you the central line. Thickness is constant here. It is subjected to anti-clockwise torque of 62.5 into 10 to the power 3 Newton mm. Maximum possible thickness of the channel section such that the shear stress does not exceed 100 Newton per mm square is. They are asking you to find maximum possible thickness, means the value of T, so that tau does not exceed this value. So let's put the value of tau this much. Okay, so which equation are we going to use? We are going to use this, tau equal to T into T by J. But first we need to find the value of J. So how do we find the value of J? J is integration T cube ds by 3, right? But if T is constant, then J will become T cube into S by 3, where S is the length of the central line, right? So beta, what is the thickness here? Thickness is unknown, so we will just put T cube. What is the length of the central line? 100 plus 100 plus 100, 300 by 3. So J will become 100 T cube. Okay. So if the thickness is constant, then this formula will become T cube into S by 3. Integration ds means S. So T cube into S by 3, where S is the length of this central line. Okay, so 100 plus 100 plus 100, 300. So J is, in terms of T, it is 100 T cube. Now the formula of tau. So tau is equal to T into T divided by J. Now what is tau? It is 100 megapascal, 100 Newton per mm square. What is T? 62.5 into 10 to the power 3 Newton mm. What is the value of thickness T? That is unknown to us. So we will just put T here, divided by J, 100 T cube. Right? So from here, T square, this T and T cube, it will become T square. So T square will come here, 62.5 into 10 to the power 3 divided by 100 into 100. Na? So from here you will get the value of T. How much is it? How much is the value of T? I am getting 2.5 mm. I think there is some calculation mistake. You have calculated the value of T square. You need to find the value of T. T is 2.5 mm. Okay. So this is the thickness. Very good, very good. 2.5 mm. So this is the required thickness of the cross section. This was from GATE 2016. Okay. Let's solve another problem. This time I want you to give me the answer. I will give you a few moments to solve. Just tell me the answer. The channel section of uniform thickness 2 mm. Again, there is uniform thickness. So they have directly given you the center line. The channel section of uniform thickness 2 mm is subjected to a torque of 10 Newton meter. It is made of a material with shear modulus of 25 gigapascal. Twist per unit length in radians per meter is. So they are asking you to find theta per unit length. Okay, so L you need to put 1000 mm. Okay, radian per meter means you need to put L equal to 1000 mm. Okay. What you need to do? You need to first find J. So find the value of J, then put the value in the equation of theta. Theta is T into L by G into J. How do we find J? Integration T cube ds by 3, but T is constant, so it will become directly T cube into S by 3. Na? So what is T? Thickness is 2 mm. What will be S? 300 plus 600 plus 300, 1200 divided by 3. 400 into 8, na? 3200 mm to the power 4. This is the value of J. 3200 mm to the power 4. Now we need the value of theta. So theta will be equal to T into L divided by G into J. What is the value of torque? 10 Newton meter. Convert it in Newton mm. So 10 into 10 to the power 3. Length. They are asking you to find theta per unit length, radians per meter. If they are asking you in radian per mm, length will be 1 mm. If they are asking you to calculate it in radians per meter, length will be 1 meter, means 1000 mm. What is the value of G? It is 25 gigapascal. So 25 into 10 to the power 3 megapascal. And J is 3200 mm to the power 4. So from here, what is the value of theta? .125 radians. Are you getting this? 0.125 radians per meter. Sorry, radians per meter. Yes. Very good, Supriya. 0.125 radians per meter. This was another question from GATE 2012. Yes. So we have solved the problem related to thin walled section. We have solved problem related to, closed thin walled problem section. We have solved problem related to open thin walled section. So I hope you guys will be able to solve all these questions in GATE, right? In GATE 2026, if you get a question from this topic, I hope you will be able to solve it. So this was all from torsion in thin walled members. There are some few more topics, but it is not possible to cover everything here on YouTube. And in the next session, we are going to cover Airy's stress function, because that is another topic from where you get a lot of problems. So tomorrow at the same time, 9 p.m. here on this YouTube channel, I am going to cover Airy's stress function. Okay. And those of you who are preparing for GATE 2027, we have also launched a GATE 2027, Parakram GATE 2027 for aerospace engineering. So you can enroll in that batch. We are going to cover entire syllabus of aerospace engineering. Okay. And I am very proud to say that we have top faculties for GATE Aerospace. We have Vinod Datuslia sir, who has been All India rank 1 in GATE Mechanical, but he has done his MTech from ISC Bangalore in aerospace engineering, and he was also recruited by GE. He was working in the field of aerospace engineering. Okay, and he is also All India rank 3 in ISRO and All India rank 4, I think, in engineering services examination. So Vinod Datuslia sir is there to teach you the concepts of propulsion. We have Vinay sir, who is MTech from IISc Bangalore, All India rank 2 in GATE 𝐂𝐚𝐿. He will be taking aerodynamics. Then I am there to teach you structures. Ramanand Bansal sir, who is ex-IOCL officer, he is going to teach you structures, the concept of vibration in structures. Shivam Dikshit sir will teach you the concepts of propulsion, some topics of propulsion he will take. Okay, and we also have Deepak Jain sir, who has been working in the field of flight mechanics for the past 8 years at IIT Kanpur. So he will be teaching you the concepts of flight mechanics. Okay, so we have the best teacher for every topic of GATE Aerospace Engineering. So if you want, you can enroll in that batch and you can start your journey of GATE preparation with us. So thank you so much. I will see you guys tomorrow, same time, same place. Till then, bye bye, take care, Jai Hind.